This is question 41 from section 2.3. We're asked to find the tangents at the point 0, 0, the origin, and at the point 1, 2 for Newton's serpentine. It's the function given by y equals 4x over x squared plus 1. And I put a little screenshot from Desmos of the graph over here. You can kind of see maybe then why it's called a serpentine. It looks like a snake that has slithered through the origin and has some horizontal asymptotes, or one horizontal asymptote there at the x-axis. So that's the graph. We're going to find the tangents now. And we know to find any equations of lines, we need points and we need a slope. Well, we have the points. We got the point at 0, 0. We've got the point at 1, 2. It's going to be two tangent lines. And next, we're looking for a slope at each of these different points. So one point here, and the other one at 1, 2, so that's the point here. Well, to get the slope, we want to think about what the slope interpretation is. It's a derivative at each of those points, so we need to differentiate this function. In other words, we need to find the derivative of Newton's serpentine and figure out what the derivative value is at x equals 0 for the first point and at x equals 1 for the second. So let's get started on the derivative. And we know we're going to do that with the quotient rule. So the quotient rule goes like this. The low function, x squared plus 1, times the derivative of the high function, which is 4, minus the high function, which is 4x, times the derivative of the low function, which is 2x. And then that's all over the low function squared, so that's an x squared plus 1 quantity squared. Let's simplify a little bit. We can distribute the 4 into the x squared plus 1. That gets us a 4x squared plus 4. Next, a 4x times a 2x is 8x squared, so we're going to be in minus 8x squared. This is still all over x squared plus 1 quantity squared. And finally then, we have on the numerator a 4x minus an 8x, or a 4x squared minus ax squared is negative 4. So we have 4 minus 4x squared in the numerator, and we have in the denominator an x squared plus 1 quantity squared. So there's our derivative, and we want to evaluate that derivative where x is equal to 0 for the origin tangent line. So let's do a dy dx at x equals 0. We put the big bar in to tell our reader that we're going to evaluate the function, and then down below on the right side of the bar tell us where we're going to evaluate. So here we go. That's 4 minus 4 times a 0 squared in the denominator, and then that's a 0 squared plus 1 quantity squared in the denominator. So that gives us what? In the numerator, 4 minus 0 is 4. In the denominator, a 0 plus 1, which is 1, square it, that's another 1. So this slope is 4, and we have then the equation of the tangent line would be y equals a 4 times an x minus 0 plus a 0. So I think I'm just going to call this line y equals 4x. Let's move on to the point 1, 2 and that tangent line. So we have the derivative dy dx evaluated where x is equal to 1. So that's going to be a 4 minus 4 times 1 quantity squared, and then a 1 quantity squared plus 1, and then all of that squared. So in the numerator, we've got 4 minus 4. That's a 0. In the denominator, we have 2 squared. That's a 4, but 0 over 4 is 0, and we have a slope of 0. So this line equation is now y equals the slope 0 times x minus the x minus the x value of the point 1 plus the y value of the point 2. Well, the whole first term makes 0, so this line is just y equals 2. So there's that equation. Here's the other one, and let's just sketch those in and see if that makes sense. At the origin, would the tangent line be y equals 4x? And I can agree with that. It would. It has a origin y-intercept. It has a slope of up 4 over 1. Then at 1, 2, is that just the horizontal line y equals 2? Yeah, it sure is. Look at that tangent line. It's for sure flat. So those are our answers to 41 on section 2.3.